So what about very short T2s? And for the last almost 20 years, we have been struggling with G-protein coupled receptors. And here you see now a 1-1 experiment spin echo on the beta-1 adrenergic receptor. We have to make it in insect cells, meaning isotope labeling is complicated. We can now do a little bit of deuteration, but there's another problem. So normally, at the moment, we use non-deuterated receptor. It is detergent solubilized. The receptor itself has about 40 kilodalton molecular weight, but in the detergent micelle, it's about 100 kilodalton. And here you see just the 1-1, as I explained you yesterday, how you would measure it. You can measure it still pretty well. Here the amide region, and here is the aliphatic region, and also the detergent. Yeah. And now when you measure the T2 here by varying the spin echo delays, you find that the T2 is 3 milliseconds something. So we can do selective isotope labeling, adding certain amino acids to the medium that are isotope labeled. For example, in this case, this is leucine and 15 labeled, glycine, valency 13, and nitrogen. And you can still observe a decent Trosi experiment, so the 1-1 coupling is still effective and so. But then we made this isotope mixture because we wanted to do HNCO. We were thinking this is still the most efficient experiment, but actually doing it as a 3D, you know, we lose the square root of 2. We rather did it as a 2D to get all the signal to noise that we can get. And this is a 2D where you connect H and N, and the N is connected to the preceding CO when it's a carbon 13. Yeah, so it's edited
by coupling two
amino acids that are carbon 13 labeled. And so this is this red spectrum that took almost a week to record on, also this should be 500 micromolar receptor. You can still concentrate the receptor. This is not a problem. Making the receptor is the problem. But then you observe a handful of peaks, and it's really not viable to do this triple resonance method anymore. And so the postdoc at the time, Shinizo guy, he did what he called the brainless approach and just mutate one residue after the other. And we were looking at valines to begin with, and there's, I think, 28 valines in it. You see that the peaks are nicely resolved still, yeah, but getting the assignment information. So he made more than 20 point mutants, and now insect cell expression means you need to create virus that is mutated and so on. But then he got 21 assignments of this, and I don't show you the results on the different ligands. They're very interesting from the function. There's a beta adrenergic receptor, it's the receptor of adrenaline in the heart muscle, and there's all the beta blockers that work with it, and agonists and so on. You can learn a lot, and I think this gave us really nice insights. But the tedious part is this assignment, and so we need more and faster assignments. And for that, we came upon an idea that we called GPS by pieces. Yesterday, you already said GPS. So maybe with Gita Pinter-Kuda, you had similar ideas, but for us, it was the assignment. And putting paramagnets around the protein to irradiate the protein, basically with a magnetic field. And in this case, we know the structure, but we want to get the assignment. Yeah. And now putting the paramagnets onto the protein, we tried for a long time. And whatever you do to the receptor, this tag is large. The receptor didn't like it very much. But then we realized that actually for our experimental system, we use a mimic of the G protein. The G protein coupled receptor couples the G protein, and there's a nanobody that mimics the G protein binding. And we can just use this nanobody and tag the nanobody. And God has made the nanobodies to survive. They are 80 degrees, 100 degrees melting temperature, and you can do anything with them. And so we can just put the paramagnets on the nanobody, then see what the pseudo contact shift effects are on the protein resonances, and put the paramagnets at different positions on the nanobody. We are completely free, actually, and then study this. And we use as the tag, this DOTA tag that was derived by Daniel Heusinger, one of the variants. And we could even, so this is attaching to a cysteine, and we could even get a step further. So it's the cysteine, and then you have 3 side chain rotamers around Chi1, 2, and 3. This total 18 possible staggered rotamers. And you see them here. They would look like this. But now we can do just on the surface of this nanobody, look at what is sterically allowed and what is not of these rotamers. And so we do a van der Waals clash analysis of these rotamers and then compare to the experiment. And what you see here is now basically the number of allowed rotamers for different positions on the surface, on the vertical axis, and this is the RMS of all the pseudo contact shifts measured in the receptor. And what you see is when the number of allowed rotamers is large, then the RMS is small, because it's averaging over many positions. But when the number of allowed rotamers is small, then the RMS gets large, so we get appreciable pseudo contact shifts. And actually here's an outlier, but this outlier is actually situated in a loop. And and it's a very, very simple analysis. You just scan the protein surface for van der Waals clashes, and it gives you a kind of reasonable hint what would be good and what not. And so we settled then on 3 positions on this nanobody, and then you acquire your spectra. These are the valin spectra, again, valin 15N labeled, and the spectra look really very good. And one should say that the detection limit is around 80 or 90 angstrom from the paramagnetic center for the shifts. So on the other side of the receptor, you can still see shifts. And then when you superimpose the individual paramagnetic spectra, they, as Gottfried explained, they fall on lines, more or less. And and that even in the crowded regions, you can more or less fit which fits to what. And so this lends itself to some kind of automated assignment procedure. We had initially for this complex 6 assigned valin resonances that we put as a starting point. We want 28, and the remaining basically come from an automated procedure. You try to estimate the pseudo-contour shift tensor and then see what fits, what doesn't fit, and so on. I don't want to explain all the programming steps. But in the end, so you get these assignments, and this is the comparison between predicted and measured pseudo-contact shifts. And then the net result is that you get right away all the assignments. And I should say this is not only a nice NMR procedure, but what our problem was, so this is the active state of the receptor. And when you do point mutations, very often you abolish the active state. So you can't even do the point mutations. But the nanobody does it all for you. And so we get these assignments there. And then actually there's a second nanobody. So this was the active form, but there's a second nanobody that binds in the inactive conformation. And you can do now the same thing for the inactive conformations and its ligands. And so carvedilol, for example, beta blocker, maybe some of, nobody of you has high blood pressure, but you may have it at home. So carvedilol, for example, get all these assignments also, and then you can from that estimate what the apo form is also, because it's not so much shifted. And so in net result, we have all the assignments in all ligand-bound forms, and then we can compare active and inactive conformations. For example, here, what we had seen before from the assignments that we had there was that these two strong shifts in helix 6, when you go from the pre-active versus active, we call it. But now with these additional assignments, we see that there's a lot happening also in helix 3. This is this helix here. And this is interesting because the crystallographers, they see that this helix 3 is not changing almost between all the different forms. All the other things also are not changing very much, but this helix 3 is particularly stable. This is described as a scaffold for the whole thing. While the other things are moving around, this stays in place. And what we are seeing is that this helix 3 has these nevertheless large NH chemical shifts. So, but what do these NH chemical shifts mean in the end? The NH chemical shifts, they depend on the hydrogen bond geometry. And I think the overall structure of this helix 3 is not changing very much. Actually, these shift changes may correspond only to 200s, 400s of an angstrom in distance, but this helix 3 is taking up the forces from the motions around it, like a pillar that is holding up other things, but you see the forces acting in the pillar here. So, and then you can go on. We had valine, but now we already know the pseudo-contact shift tensors. You can just put in another amino acid, any type of resonance you're interested in. It works right away for tyrosine. And meanwhile, I think we have also another 3 amino acids. We have about 90 assignments nowadays in all forms of the receptor. Okay, so with this, I'm done with this. So I hope you found something useful in it.